Okay, how are you guys doing on the lab? Who here has not finished? Just out of curiosity, okay. Has anyone not started on the test benches? Okay, so most of you at least started on the test bench. Hopefully, so our lab is later today. Yeah, that's right. Hopefully we can get everybody checked off in this lab and start lab 2. So I covered lab 2, right, for you guys over what we're doing. It's basically the same thing. Shouldn't be too painful once you finish lab 1, hopefully. Today, again, I believe I'm going to keep this short. I think it's going to be just under an hour, I hope, for the lecture, so that you have some more time to go work on this, because really understanding this lab is incredibly important to the rest of this class. The material today, we're just going to start it on chapter 3 that kind of gets into the nuts and bolts of how these programmable logic actually work, so that you understand kind of what's going on behind the scenes. So it starts off, this chapter does, with kind of a history of programmable logic. I'm not going to go too deep into that because it seems silly to test you guys on history, and so there's better uses of our time. But some of the main takeaways is that in the early days, most programmable logic was programmable one time. You couldn't just erase it and start again like we do with our FPGAs. You programmed it at the factory. And if you look at some of the most obvious early programmable logic, one of the most common ones is still around, which is ROM, right? Read-only memory. And these ones are called mask programmable, or in the early day, they were mask programmable devices. And what that meant is they'd make a mask, which is a way of delivering charge to the circuits that they would then remember and stay configured. But you couldn't do anything to undo that, and the masks were very expensive. So it made sense when you were making 1,000 or 10,000 devices and then selling them as retail. But other than that, they weren't really practical for prototyping. Eventually, they kind of went on to start building up other ones, like EPROMs. You've probably heard the term. And early EPROMs, these EPROMs are EPROM with one E. And they could be erased using UV light. And then you could program again. So you'd have to open them up, shine some UV light on them, start again. And then they developed EEPROM, which then could use just charge. You would just deliver charge to these devices and you could reset them and reprogram them. So they slowly marched along, got better until now, where that's basically what we're using with, where we have the USB cable hooks up to your FPGA and it just sends a series of bits that gets converted to charge, which then is translated into the way these gates are connected on the FPGA, which creates your logic. And we'll talk a little bit about what that structure of the FPGA actually looks like, but we're going to start with ROMs. Then we'll go into PLAs and PALs. So PLAs are programmable logic arrays, and PALs are programmable array logic. Silly reuse of names, but it makes a little bit of sense because a PAL is really just a specific type of PLA. And we'll get into what that means and why later. But that's all we're looking to get through today, is PLAs and PALs, which are both a subcategory of SPLDs. So PLD, programmable logic device, is like the big family name of everything. SPLD is basically what they call it when it's simple, right? A simple one, so it has a few gates, versus a CPLD, which is complex programmable logic device, and it has more gates. And then you get up to an FPGA, which has the most devices. There's a table that talks about that on page 140. But it's kind of, right, simple, complex, and then FPGA. And that's what we're dealing with now. One thing to keep in mind as I go forward, in case I forget to say it later, PALs and PLAs in general are almost never used anymore. They're all but extinct. You might encounter them in industrial design. So if you go into manufacturing kind of thing, and they have control systems maybe, or big machinery, you might run into a PLA. Okay, but ROMs is where we're going to start because that's the earliest and the simplest. So a ROM is really just a device that, sorry, I have to keep the blackboard or the camera in mind so that they can actually see what I write. And I was told that green does not show up very well. Okay, so if you have, right, starting to look like a truth table, a device, a memory, and you program it so that if you give it a certain input, it gives you a certain output, right? So right, so it has two inputs, one output. I give it an A and a B, and it just outputs that value based on some lookup table, right? That's fairly simple, straightforward logic. And that's all a ROM is a series of what we call lookup tables, LUTs or LUTs. And you'll see them defined as, you'll see something like it'll have 8 words by 4 bits. And that's how they'll describe how big this memory has to be. And so you can look at how large your ROM has to be, because there's no tricks, there's nothing clever going on about it. It's just straightforward lookup tables. And so here, what the word is talking about is how many rows we have, and the bits is the number of output bits we have. So all it comes down to, and this is a useful equation, is 2 to the n by m, or the bits is m and the words is n. So we have here, right, we just have 4. Sorry, let me make sure I'm doing this right. Yeah, so you can, where n is not 8, I'm jumping ahead. It's just 2 to the this. These are n. 2 to the 2. So this is 4 words, right? Where n is the number of inputs. And then m bits, we just have 1. We can go on and do something bigger. And the book that uses it, and just so the word is in direct relation to an output. So that's a word, that's a word, that's a word. But you could have more or something that has other outputs that you have a Z1 and a Z2. So in this case, right, I'm programming a XOR gate and something else that is doing a lookup. But you can even go in and start programming something that is like a full adder or an encoder or something like that, that starts to get a lot bigger. So if we look at this example, I'm not going to write this all out. This is actually an example from the book. And it's just saying we have a lookup table and so on and so forth. And it's going to have some output and so on and so forth. That you give me these inputs, get these outputs. This could be, as I said, an adder. You just have to go and figure out what is the truth table for a full adder, and now it's a full adder, as long as you program it up right on the initial programming. Let's see. Actually, yeah, this one actually has a full adder in it that I can kind of go through just to show, oh, a couple of it, just to show how it is. So as our inputs, right, we're going to do just a 2-bit adder. So sub 1 is going to be x1, x2, and the other input is y1, y2. And then we need, if we're adding 2 bits, right, we need a 3-bit output, because you could end up with 3 bits if you add 1, 1, 1, 1 together, right? And then you just start assigning these values to it. And so on and so forth, right? And start looking at what those summed outputs. Obviously, if I'm adding just zeros together, I get 0. Again, nothing fancy, right? It's just 1 to 0 is still 1, until you get down to 1, 1, 1, 1, in which case, there's your sum, right? And so what that's going to do is you're going to have this block with 3 inputs, or sorry, 2 inputs and 3 outputs. But each of these inputs is a 2-bit array, right? Into those. So you put these values in, this does some math. And, well, no, I take that back. It doesn't do any math. It just looks up what you told it's supposed to be and outputs it. Done. That's all a RUM is doing. And it's not especially clever on the internal workings, but it is useful. They get more useful because you can actually turn these guys pretty easily into a state machine. So we didn't do too much in the review on building the physical components of the state machine, but this is sufficiently easy that I don't think we need to worry about that. So if I have a present state, next state, and what the output is, and this is just S0, S1, we have 7 total states. Our next state is going to depend on what the input is, right? So it's 0 or 1. And our output also depends on what the input is. What kind of state machine is that then? Just a generic type, right? There's 2 kinds of potential state machines. What has this table inferred that our state machine type is? The Mealy state machine, because the output depends on the input and not just on the state that we're in. Okay, so here we go. in the state machine. This is just a BCD to XS3 code converter. You don't need to know that, but it's the example back from chapter 1. It goes through kind of the design of this state machine. But we're just going to take the state table and assume that we're given this, and now we need to design a state machine off of a ROM logic. And so now it just has to look up what the inputs are, what the current state is, and give us outputs that we desire. So the way you do that is you take a ROM, right, which is just lookup tables. You hook it up to some, these are all just D flip-flops, DQ flip-flops. You throw some of the outputs into those guys. You of course have to clock all of these, right? But I'm not going to clock them. I'm not going to draw the clock, just to keep it a little clean. We know that the output is so the output of the state machine is going to be your next state. The present state is going to be what's being looked up. So these are all going to feed back around as the inputs to the ROM. Okay? And so what that's going to do is on a clock, it's going to load the next state into present state, right? So as long as the lookup table is outputting the right values for the next state, we're good. But we also need X, right? Because we need that input. So now it's going to do something with X and present state. So if I'm currently at state 0, and this X input, so I see state 0 at these inputs, and X is 0, then it looks up and outputs S1, state 1, into Q1 to Q3, right? If X is 1, it's going to do the lookup and output state 2 in Q1 to Q3. Then on the next clock period, D gets clocked into Q, Q feeds back around, and now the new lookup table says, oh look, I'm in state 2, say. And now it doesn't care what X or 0 is. It's going to be, next state is going to be S4 regardless, according to the lookup table. It's just going to change Z, which is some other output, right? And that's what you're looking for. That's how you design a ROM-based state machine. Does that make sense to everyone?
What's the dash gun?
It just means that it's a don't care essentially, in that this can't happen. If you were to be in a situation where you were in state 6 and you gave it a 1, it would be confused because that meant you hooked up the wrong logic as the input. In the case of the BCD to XS3.
Same with like state 7, since you've got the 3 like Q1, Q2, and Q3, there'd be a state 7, but it's just like lost.
Well, it just only needs.
It should have never get to those.
Yeah. If you did the input right, it will never get to this. So you may do something, and you can be in a situation actually in the state machines we're designing for the lab, where as long as everything goes right, you never have to worry about certain situations. But you may do something like this goes to an S, back to S0 anyways, right? Because we don't want to get stuck somewhere in case something goes wrong. And then you're going to add an extra output and maybe call it E. And all of these are 0, and this is 1, right? And that's an error reporting saying that you just did something really weird and you need to rethink whatever you just did, right? That can happen if, in our current system that we're designing for a lab, do the start bit, you go through all of the data. It's supposed to go back high for the stop bit. So we can sample the stop bit, make sure it's high. And normally we want to assert ready, saying that we've received all the bits. But if I get to the stop bit, I measure it, and it's 0, I still want to go back to state 0, back to idle. But I don't want to assert ready because it's clearly whatever I just got was garbage. Okay, so that's it for ROMs. They are the simplest of programmable devices because there's no intelligent fancy tricks to get to them. Programmable logic arrays are a little bit more interesting, and for this, I'm actually going to try to pull up the document cam because it's a little bit easier just to show these rather than spending forever drawing these circuits. Hopefully it works. I had some struggles with this in the other lecture, but so apparently the camera and this have too close of codes. So if I turn this guy on, it turns off the camera, but I can easily turn back on the camera. Oh, come on. It's almost working. Yes, it's pointing right at my drink. Oh, come on. It's there, I promise.
Almost there. Half there.
It's almost, it's thinking about. I think it's trying to like auto turn off because it doesn't think it's bright enough or something ridiculous. Okay, let's turn off some more of these lights so you all can take a nap, right? That makes perfect sense.
I like naps.
Yeah, me too.
They're good. Oh, that looks good. It's not.
Oh, come on.
Maybe it's just the projector. It's like, yeah, I'm just done.
It might be. Let's see. What do I do with the projector?
Because it's still projecting to your screen. Oh, that doesn't look. Oh, okay.
Yeah, that's an issue. Okay, let's try this without turning off the camera. No?
There's something is. Oh,
It's like almost there and is really confused. So last night it had an issue like this, but not this severe. Come on, it's not rocket science technology. And so it's like, okay, if I zoom in, maybe not. Okay, looks like I'm going to be stuck doing a bunch of drawing. I'm sorry, that's going to extend that. Okay, so I guess I should turn it off, huh? And try not to turn off the camera, maybe. Nope, I can turn off the camera. I cannot turn off the projector. Okay, there we go. We got the projector off. Let's get the camera back. Nope. And hopefully we haven't broken the Zoom recording. Okay, if you were watching at home, the video turned off. Hopefully the audio didn't. You didn't miss anything because it failed miserably. Okay, so let's say that we have a PLA, programmable logic array. The way these guys are laid out is that they have vertical inputs, and then they each take an inverter like so. So C comes in and goes down and also gives an inversion, right? So that I have access to both C and C bar. B does the same, and A does the same. Then, so these are your input rows. Then you're going to take AND gates and these AND gates are going to wire up programmatically to your inputs. What I mean by that is these AND gates are what gets programmed. So you can tell them to say, I want you to go connect to A. And then I want this one to go connect to B bar. So the example is in the book. It gives you a series of equations. I don't need to write the equations up right now for you to understand the concept of how the programming is done, right? So out here, the output of this then is A and B bar, right? I could tell it during programming to connect up to other ones, but this works as well. And then the next row would go on to program, say, A and C bar. Okay, now there's a next part of this where each of these outputs has to be wired up to a series of OR gates, which I'm already bad at drawing the normal direction, so they're going to look terrible drawn this direction. And then these OR gates could go say this one's going to connect up to AB bar and AC bar. Now I have this term this is AC bar, where the output is AB bar or AC bar, right? So what you'll quickly notice is that all outputs of PLAs are implemented as a sum of products. So this is helpful because if you use K-maps, right, you can easily generate some product terms. But there is something interesting that happens in a PLA that doesn't really happen in any other device. Well, not in a device that you'd care about this happening. Because these really can have 20 potential gates at the output, and that would be it. They can be very small. So you may need to optimize the logic some. And what's interesting is that the logic optimization for a PLA is different than the logic optimization for like hand building a circuit. Because you want to look at these terms, and you don't necessarily care about them being the simplest term. What you care about is that these OR gates share these terms, right? Because if this one is AB bar and something else, I've reused this AND gate, and I don't have to repeat an AND gate. So you're going to start looking for a different type of simplification. So this is where I really wish I had the projector overhead, because this is going to require an obnoxious amount of drawing. Okay, so let's say I have 3 equations, and I put them into 3 different K-maps. I'm going to grab one of these black markers, see if it works. Let's see how bad it is. That's not too bad. Sorry. Okay, good enough. If I go much further left than this, apparently it's off the screen. So I guess that's important to know. Okay, so in a normal situation where we're trying to individually minimize each of these terms, right? So this is F0, F1, F2. I would go in and I would look at this and say, okay, so I've got a big block of 4 right here. Let's circle that. Right? And then I would go and I would do this circle, and that guy would wrap around. But for a PLA, because I want to share these ANDed terms, what I'm actually going to do is start looking at circles that I can make in all of them, or at least in 2 of them. So instead of these 4, it's actually more useful to make this circle and that circle separately, because shared terms, right? And even over here, another shared term. So I'm now minimizing my AND gates. Similarly, this wraparound is actually really good because it's a shared term. These 2 ones, rather than being a 4 across the bottom, which would be a good one for simple manipulative logic, is the outsides and this one and those ones. Again, shared terms. So what we start seeing is that these shared terms, when we start getting them, the AND gates that we see start getting minimized, and the size of our device gets minimized. So the PLAs are different in that regard compared to other logic. So once you have them, this minimization, shoot, I shouldn't have erased all of them. So one drawing way that I want you guys to see, because it is useful and nice, is if I have an input, actually I'll draw 2 inputs just for the sake of it. To simplify the drawing, because everybody hates how much drawing they require. This AND gate would have one line, and then you would just put a dot where you wanted to connect, right? So this implies A and not B, right? But they'll take it a step further, and they won't even draw the AND gate. They'll just draw vertical lines here. So now we're implying A and not B, and then you have this or that. Oh, sorry, this or that, right? So if you share a horizontal line, you're ANDed, and if you share a vertical line, you're ORed. That makes sense in that notation. It's a weird but useful notation. So the way the book explicitly calls it out is like so. This is functionally equivalent to that. I really don't want to draw the whole thing. I highly recommend going and just looking at figure 3-17. I think I've explained enough that it will make sense. It's on page 152, and it's an implementation of a full adder in PLA logic. And you can imagine that it starts getting a lot of these horizontal lines going to AND gates, and so it's got 4 ANDed terms into OR gates, and so on and so forth. And remembering that, because I know some people forget, if I'm stuck with only having 2 input AND gates, right? I can extend the AND gates simply by doing that, right? That's now a 4 input AND gate. And I can keep fanning that out. Yeah. So PALs are the same thing as the PLA that I just described, but only, I have to make sure I do this, say this one right. I think it's only the OR gates can be programmed, but I'm going to make sure of that, and I got ahead of myself, so I got a little bit lost. Let me make sure. I don't want to misinform you guys. That would be bad. I don't know where it is. I know I underlined it and I'm just going crazy, I think. Only the AND gates are programmable, yes. So you can't program the ORs in a PAL. In a PLA, you can do the ORs and ANDs. In a PAL, you cannot do the ORs. This makes them less expensive to design because you only have half as much programmable, but it also means that you can no longer share AND terms at the OR gates because the OR gates are predetermined. Yes. So one thing that you do have to keep in mind sometimes when designing a PLA or a PAL is that your logic could be driving, like your AND gate could be driving a whole bunch of OR gates. And if you start getting to really large OR gates, you can start having too much of what we call a load, right? And your logic can slow down. So you do need to be aware in large PLAs and PALs that if you have too many OR gates, you may have to deal with a slower clock. Rare problem, but it does exist. Going forward, right, I mentioned that we have this term, the PLD, which is the generic form of programmable logic device that encompasses all programmable logic devices. On page 154, thereabouts, really starts on 153 in section 3.2.4. It really goes into kind of a deep dive of one specific type of programmable logic, and it describes to you how the logic programming is done. I'm going to be posting the homework 6, I think is what it is tonight. And I'm actually going to have you go and read that section as part of the homework. And you're going to implement what they call a macro cell, which is one of an output macro cell, which is one of the devices that actually helps you program the device. But you're going to do it in VHDL, so it's pretty easy. And that will help you understand what it is doing internally to configure these gates. But I'll do that as homework. And it's kind of an interesting one. And don't worry, I'm actually dropping one of the existing homework problems off of that and replacing with that one because I think it's more useful. Okay, so the good news for all of you is that's all we had to get through for today to stay on schedule. If you have your laptops and whatnot with you, I will stick around for the duration of class to help you with the lab. If you don't, you can use the time to work on other homework, whatever it is, to get ahead so that you can spend some more time on the lab later. I do want you to get ahead. I do want you guys to succeed on this lab. But that's the main push of today's class. Any questions on the material first? Okay. Start raising your hands and I'll help you individually on the labs. Yeah. So Jake. Okay, go back to the other window. So that's clock 100. Where's TV clock? Yeah, so go back to that. Where is 100 megahertz in here? So that's the top VHD, and that is what's defined as mine. Are you running the receiver test bench on the whole top VHD? Yeah. Or are you just running it on the receiver? Okay. So I think it might be confused. Try creating a project that doesn't have top VHD in the project. Because there's this terminology that is kind of intrinsic to VHDL and Verilog both, where if there's something named top VHD, it assumes that it's the top level, and that's what it wants to work with. And everything else is kind of ancillary to that.
Okay, so when we were doing the test bench, we were not supposed to do that.
Correct. Yeah. So maybe you can just remove top.vhd from the project and just run it on the component. But I think it's getting confused because it appears to be pulling nets from top VHD, which you don't care about. Let me stop this recording video.
Already I never used. That's why it's